Hey guys, I'm not totally sure what happens there. It says that there was a connection failed. I'm not sure if maybe it was my iPad or whatnot. But anyway, I'll just create and go through what I was going to go through right now, and I'll just upload this onto YouTube for you guys. So firstly, as far as complex numbers, if you've already watched some of those videos, you already have a clue. Pretty much what I'm just going to go through right now is just do one of each type of question. So you got everything you need for the first exercise in one video in concentrated form. If anything's a bit confusing and you need to see anything in a little bit extra or further detail, definitely check out the videos that I put up and it will go through each thing in more detail. But the idea with complex numbers is, the real number system, the one that we use, it's not every number that exists, right? If you think about the number plane, you got 0, 1, 2, you got the negative numbers, the fractions, all this stuff in between, the square roots, pies. They're all numbers that exist somewhere along this number line, but that's not all the numbers. And we can see that, for example, if I asked you to solve this equation here. If I asked you to solve this equation, you could go ahead and do it. It'd be no dramas, right? X would be the two different values, plus or minus 3. Again, that's a real number. 3, negative 3, they're both numbers that we're familiar with and that we've been using previously. If I ask you to solve this one, x squared is equal to 5, for example. Again, this also has solutions. Mind you, you might need to be in year 8 before you sort of start really seeing square roots. But yeah, it'll still have two solutions, plus or minus 5. If, for example, I asked you to solve this equation, every single person, including those that are doing the Extension 1 course, would look at that and say, hey, there are no solutions. Or what you often hear teachers say is there are no real solutions. And the reason for that is, well, firstly, there are solutions, but the solutions aren't any numbers that you've previously learnt. And that's where we need to go to what we call imaginary numbers. By the way, they're called imaginary numbers, but they are actual numbers. They're just a different type of number than what you've seen previously. In this particular case, our solution would be the square root of minus 1. And again, if you were limited to the real numbers, well, you'd say, well, there are no numbers that do that, right? What number, when you square it, ends up giving you a negative 1? And the answer is there is a number to it. It's what we call an imaginary number. And we call it I. Whenever you see in the Extension 2 course just an I on its own, that is a number. And I is actually the square root of minus 1. It is a genuine number. It's used in lots of questions, engineering, all sorts of different applications, physics, chemistry. You won't see it at the HSC level in any of those things except Extension 2. But complex numbers are used right across the spectrum. So in this particular case, yeah, I guess, this is the start of complex numbers. I is this brand new number, which is the square root of minus 1. What's interesting about it is if you're working out what I squared is, well, of course, that's the square root of minus 1 squared, which is going to end up giving you 1. If we were working out what I cubed is, right, it would be like, the square root of minus 1 times the square root of minus 1 times the square root of minus 1. These two would end up just becoming a minus 1. So it ends up becoming minus I, right? Remembering that, hey, the square root of minus 1 is I. So this is what I is. Now, complex numbers and the numbers that we're going to see, they may have a part of the number may belong to our normal real numbers. And part of the number may belong to, you know, the imaginary numbers. So what you actually often see with complex numbers is, you know, like for example, 2 plus I, it has a real and imaginary component. So let's say we have this complex number 2 plus I, and we have another complex number I'll call Z2, which can be like 3 minus 4I. Okay, so we've got these two complex numbers. Now for the first exercise, you're going to need to do all the basic operations. So we're going to learn how to add, subtract, times, divide, and square root complex numbers. That's pretty much our job for the first exercise. So all that stuff that you did in primary school with the real numbers, you're going to learn how to do right now with the imaginary and complex numbers. Just a couple quick things before we go on ahead, which may or may not be explained in the other videos that I've posted. If you see so let's say we have this new complex number, just different to the ones I just put up here, 3 plus 2i. If you see Z with like a bar above, that's referring to what we call the complex conjugate, which would be 3 minus 2i. All that happens is with complex conjugates, it's the exact same complex number, except the imaginary part has the opposite sign. It's extremely useful for, you know, calculations and operations and that sort of thing. So you will see some questions in the exercise that ask you, for example, it might be like, hey, what's Z plus Z bar, right? And that's just asking you in this particular case to add the complex number with its complex conjugate. And funnily enough, it adds just like normal, to be perfectly honest. In this case, you'd actually end up with just a real number. The imaginary components end up cancelling. But anyway, so just firstly be aware of the complex conjugate. And it works very much like, you know, when dealing with surds and dealing with the conjugates there. You remember, like, if you had like some, for example, irrational, like a fraction with an irrational denominator, and you were asked to rationalize the denominator, do you remember how you'd multiply it top and bottom by its conjugate? It's exactly like that, but in this case, we're dealing with complex numbers. Anyway, let's get on to the basic operations and the main point of this video. Firstly, how do we add? Well, you already just saw an example. Very much just the way you think. If you're going to add two complex numbers, it works just like normal algebra, really, where these i's, you know, you can just view them as like pronumerals if you wanted. Anyway, you're going to add your like terms, so to speak. You can think of it in terms of that. Okay, so that's how you add complex numbers. So no real tricks there. How do you subtract complex numbers? Oh, by the way, worth noting that just like with normal adding of like your real numbers, if you swap the order, right, you still end up with the exact same number. Complex numbers, you know, work very much just like, you know, just your normal real numbers. You know, lots of the same rules sort of apply. So the order in which you add makes no difference. Subtracting will of course make a difference. In this case, we're doing Z1 take away Z2. So you got Z1. We're taking away Z2. Right, so we're going to take away all of that. So we end up with a -3. Two negatives make a positive. And of course, collect your like terms. And that's how you subtract complex numbers. Yeah, so pretty simple. As far as multiplying, again, let's say we're going to multiply these two complex numbers. So here you've got 2 plus I all times by 3 minus 4i. So in this case, you just expand it just like normal. Use your FOIL or whatever method you normally use. Just pretend you're in advanced maths or year 10 even, and just go ahead and multiply. This last one is pretty interesting. You end up with minus 4i squared. Definitely super worth noting, I squared, remember, is the square root of minus 1 squared, right? That I is the square root of minus 1, so I squared would actually be a negative 1. So don't freak out when I say we end up with some like terms there in the middle. This ends up becoming a minus 4 times minus 1. It actually ends up becoming a plus 4. So, that's how you multiply. So when multiplying, just be aware that it's pretty common to end up with an I squared at some point. I squared ends up becoming a minus 1. Dividing. So let's say we're going, Z1 divided by Z2. So you got 2 plus I all over, I actually figured it was 3 minus 4i. Okay, so if you want to divide these, you don't worry about, like your synthetic division, that's, for unknown numbers, your polynomials, that sort of thing. Both of these numbers are known, right? Like I'm saying, they're not the normal counting numbers. You don't need imaginary numbers to count the number of sheep there are in a paddock, but they are real numbers. They're known numbers. So we're just going to go ahead and divide them. In this particular case, ultimately, what makes this a little bit confusing to our minds is having imaginary components on the bottom, right? It makes it look messy. So you can probably guess, if you want to divide, our step is actually going to be to get rid of the imaginary component. And this is where, just like with surds, we're going to multiply by, in this case, the complex conjugate. So we're going to times top and bottom by 3 plus 4i. On the top, this is, nothing particularly interesting. Just go ahead and multiply like you normally would. Actually, I think we've already multiplied the two numbers, right? Oh no, this is plus 4i, slightly different. Let's just go ahead and do it. You end up with a plus 3i here, and you end up with a minus 4, right? With that final term, it was 4i squared. Remember, I squared is minus 1, so you get a minus 4 there. So I've multiplied the top. The bottom is super interesting. Check it out. This is worth noting. Instead of expanding like normal, can we not just use difference of two squares shortcut? 3 minus 4i times 3 plus 4i. Like, you can go ahead and expand it all out, and you're going to end up with the same thing anyway, but we do have the difference of two squares shortcut. First term squared minus the second term squared. And of course, worth noting, I squared is minus 1. This becomes a positive 16, and you end up with an answer. Yeah, so anyway, you expand it out, and you end up with 25 on the bottom. So what do we end up with when we collect 2 plus 11i all over 25? That's how we do division. You can just leave it like that, or you can break it up into its real components and its imaginary component if you want. But that's how you divide your two complex numbers. Just multiply top and bottom by the complex conjugate. All right, and the final thing I need to show you is square rooting a complex number. Let's say, for example, let's say I give you this complex number 1 plus root 3 I. I'll do a square root because, you know, people freak out when they see that, but everything's cool. Let's say you want to square root this particular term. The way we square root complex numbers isn't so bad, but there is a trick that we use, right? Because it's not just as simple as, you know, square rooting a real number, you know, or even, you know, something like the square root of 7. That's even easier, right? Because it doesn't even square root. You just leave it as the square root of 7. What do you do with complex numbers? Well, what we do is we say, hey, let, in this, sorry, I'm trying to, okay, so let Z be, you know, A plus BI, for example. And so, let me try and remember exactly. All right, so, okay, this is right. Okay, so we're going to let the square root, sorry guys, I'm going to not use Z. Oh, you can use Z if you want. Okay, then I'll call this something different. Okay, so we're trying to find the square root of this number here, right? So let's say you've been asked to find the square root of this number here. Well, we'll let the square root be, well, I guess Z, but here I'm sort of moving away from it. Let's call it W. Let's say W is the square root of this. So in other words, what that means is, if W is the square root of this, then that means W squared would be 1 plus I root 3. Do you agree? So if we're going to say, hey, we're going to let W be the square root of this. By the way, I'm putting the I at the front of the square root of 3 here, just to show you that the I is not like inside the square root. I actually prefer to write it like this, but then it can be a little bit confusing. Is the I a part of the square root, or is it, you know, and it isn't a part of it. So that's sort of why I put the I in front. So if W, over here, if W is the square root of this number, then of course that would imply that W squared is equal to 1 plus I root 3. Right, and that's where we're at here. Okay, so back over to my working out. So you just let some generic complex number be the square root of whatever you're trying to find. So then you can say, well, that complex number squared is equal to the thing. Now, we're going to, yeah, as I said, we're going to let this W be A plus BI, right? We're trying to find what this square root is. So what actually is, you know, W squared? So if W is A plus BI, W squared would be this, of course, which would give us A squared plus 2ABI plus B squared I squared. And of course, remembering I squared is actually a -1. Okay, there it is. So this is what W squared is equal to. And for our particular question, we know that W squared is going to be equal to 1 plus I root 3. So these two things are equal to each other. So by equating real and imaginary parts, if these two things are equal to each other, right, I'm referring to this line right here, if these two things are equal to each other, then that must mean A squared minus B squared is equal to 1, right? Those two real parts must be the same. And two AB must be equal to root 3, right? That is, the two imaginary parts must be equal to each other. And by doing this, what we actually have here is two equations, two unknowns. We're just going to solve simultaneously to get our answer. It's as simple as that. So this now ends up just becoming a simultaneous equation. So, in this case, how do we solve this simultaneously? Let's create a bit of extra space for ourselves and take this over to a brand new page. Okay, so first step I would be doing is I'd be rearranging, maybe let's b equal root 3 all over 2a. Okay, and then what I'm going to do is sub that into 1. So I'm going to sub into equation 1. So you end up with a squared minus b squared, which is actually going to be 3 all over 4a squared, right? Hopefully you can see I've just squared this here. And that's equal to 1. And we just go ahead and solve this equation. So 4a to the 4 minus 4a squared minus 3 is equal to 0. Does this even factorize? Let's check it out. 4 times 3 is a minus 12. Oh, do you know what? I'll use cross method. What is that? 2a and 2a. Does this work? 6. Yeah, minus 6 plus 2. Okay, so factorizing this, we end up with a 2a squared minus 3 2a squared plus 1 is equal to 0. And then go ahead and solving this, right, to find what the potential values of a are. Right, notice we're trying to find what the square root of this number is. And that's going to be, we're trying to find w. We need to find the value of a, we need to find the value of b. What is a going to be? Here we can see a is going to be, a squared will end up being 3 over 2. A will be plus or minus the square root of 3 over 2. That of course implies that b would be equal to, so subbing that back into our expression for b right here. So what is that? Root 3 over 2. So b is root 3 all over 2a, and of course I'm dividing by the a here, in other words multiplying by the reciprocal. I'm doing that because there's some nice cancelling. B would be plus or minus 1 on root 2. Therefore, telling us that w, right, the square root of 1 minus root 3, or whatever the original question I just randomly created would be it's a plus bi, which of course a is plus or minus root 3 over 2, and b is actually a plus or minus 1 on root 2. And so that could be rewritten a little bit neater. Throw the plus or minus out the front. You could even throw the 1 on root 2 out the front as well if you wanted. But so therefore w would be plus or minus root 3 on 2 plus 1 on root 2 I. So they're the two possible, and just, like when you normally square root a number, right? There's two different possible values. Just like here, we've got our two different possible square rooting values. So hopefully that makes sense. Final last few things, sometimes they just ask you to like show different results. For example, something like, well, something we already looked at, z plus z bar. You might get a question that says, show that z plus z bar is real, like for all complex numbers. And with questions like this, what you end up doing is just let z be just some generic complex number, a plus bi, x plus iy, or more often you'll see, iy, see it written like this, and just go ahead and do what it says. Therefore, z plus z bar, or z conjugate, would be x plus iy, plus what is z conjugate? Well, that is x minus iy. And here you can see you end up with an expression that has no i's in it. The imaginary part's cancelled. Thus, z plus z bar is real, right? If you're trying to show that something is real, you're trying to show that the imaginary parts completely cancel out. Or if you were to potentially get a question that was asking you to show an expression is completely imaginary, like for example, z minus z bar, then in this particular case, you do the same thing. Maybe let z be, pick whatever pronumerals you want, right? It doesn't matter. And just go ahead and just sub it in to the expression. Just go ahead. In this case, we're subtracting complex numbers. The a's end up cancelling and you end up with two lots of bi. People write it as like 2ib, or however, it actually doesn't really matter. I wouldn't put the I at the front in this case. Always put your sort of numbers. I'd put the real number first. Probably, I don't know, you'll probably see it written like that more often than not. But so just as a final thing, you'll see some questions like that where if they don't give you the complex number, just create a generic complex number and just work from there. All right, hopefully this made sense. Hopefully I didn't ramble too much. I know I was definitely rambling with the square root. I actually haven't done a question like that for a couple years, so it actually took me a moment to try and remember like how I set out the working out. But ultimately, if you're trying to find the square root of a number, or even, and this was, like a complex one, right? Because we're trying to find the square root of a complex number that already had a square root in it. So this was theoretically, as hard as it's going to get. Same thing, right? Just sort of, create this new complex number, a plus bi, x plus iy, whatever you want to call it, and just let that be the square root. So when you square it, when you square root, you'll always end up with these two parts here. And these sections here will just be the real and imaginary part of whatever the number is you're trying to square root. And so you're always left having to solve a simultaneous equation, which is always the same as this one here. The only subtle difference is that will be a different number and that will be a different number. And like as far as adding, subtracting, multiplying, and dividing, they're all pretty straightforward. All right, best of luck with it all, and I'll see you for the next one.